And so let me first show you what we did last week, right? So let's go. Okay, so we were discussing about basis vectors. Let's go back. Let's go back. Okay, let's go further back. So let's go to. Okay, so we were talking about subspaces, and then we defined something called linear combination, right? So if we have these vectors, then any vector of this form is called a linear combination of these vectors. Then what did we do? Then we defined something span. Span, what does it mean? So if we are given k vectors in a vector space, then their span is the set of all possible linear combinations, okay? So we defined what linear combination is. So span is all possible linear combination. It is easy to see that this set is not just a set, but it is a subspace of this vector space V, okay? So no matter which vectors you take, the span is always a subspace. Then we did some examples about these things. And then we talked about linear dependence and independence. So for example, span of this set and this set are actually same. And the reason is, you see, so these two vectors can be combined to obtain this third vector, which means this third vector is not really necessary in this span because it doesn't add any new information to this span, okay? Because it can already be obtained as a linear combination of these two vectors. So in a sense, these three vectors are linearly independent, dependent, I'm sorry, okay? And the formal definition goes like this. So if you want to check whether these vectors are linearly dependent or not, then you form this linear combination, and then you try to solve for these scalars, a1 to ak, okay? If the only solution you get is a trivial solution, which is a1 equals a2 equals ... ak equals 0, then the vectors are called linearly independent. And if you get a non-trivial solution, then these vectors are called linearly dependent. Okay, so this is a general reminder of what we did, and we did some examples of this. And then we looked at this notion called basis. Okay, so given a vector space, we want to find a basis. So what does basis mean? Basis means a set of vectors, okay? And we want these vectors to be both linearly independent, and we want their span to be V. Okay, so linear independence here really ensures that so this is a minimal set of vectors. You cannot, if you add more vectors to it, you lose linear independence. And this ensures that there is just right amount of vectors, okay? So if you remove one of these vectors, you do not get the span. So you cannot add more vectors, and you cannot subtract any vectors from a basis. That's the issue of the basis. And then we looked for basis of some vector spaces. So standard basis for R2 is these two vectors, because you can write any vector using these two vectors, right? This is the I vector, this is the J vector. So in R2, in the plane, you can write any vector by using these two vectors. And if you can, and you cannot remove any of these vectors. If you remove any of these vectors, you do not get the span. And you cannot add any vectors to this, because if you add any vector to here, you can already obtain that vector from these two, so that you lose linear dependence. Okay, so that's it about the basis vectors. So these are the things we did before. Okay, so the number of vectors in a vector space is called dimension. So it can be shown that dimension does not depend on your choice of bases. So any choice of bases must have the same number of vectors, and it equals the dimension. Okay, so if we go back, so for R2, for this vector space, the dimension is 2, because a basis has 2 vectors in it. Okay, or if you look at the standard basis, this is also a basis which contains exactly 2 vectors, so dimension is 2. And R3 has dimension 3, and Rn has dimension n. And we looked at other things. For example, for P2, this is a basis. We showed that this is a basis, right? Which means the dimension is 3. So dimension of P2 is 3. And dimension of Pn is n plus 1. Okay, so there are also infinite dimensional vector spaces, which is very important for mathematics, but we won't be doing them. What else? Okay, and then last time, what did we do? Okay, we did some examples about these things. And finally, we did this homogeneous systems, right? So homogeneous systems means what? So this equation, if A is a matrix, this is a m equations in n unknowns, okay? So this is a homogeneous system. If the right-hand side is 0 vector, this is a homogeneous system. And the solution set of homogeneous system is actually a subspace. Okay. Then the solution set is really called null space of the matrix. This is a definition. This is a formal definition. And the dimension of the null space is called nullity. Okay, then we looked at this homogeneous system, and if the reduced row echelon form of the matrix is given by this, then a basis for the solution space is really spanned by these so we can see that the solution is so if we write the solution, we can see that the solution is spanned by these 2 vectors. Okay, so we can find the nullity of A. And for non-homogeneous systems, if the right-hand side is not the 0 vector, then the solution set is not a vector space, unlike the homogeneous case. In the non-homogeneous case, the solution set is not a subspace, okay? Okay, that's what we did. And today we have a small section, so I'm gonna cover some of the things about chapter 4, and then we're gonna finish our discussion of chapter 4. Today we're gonna talk about 4.8. The title of the section is Coordinates and Isomorphism, but we're only gonna talk about the coordinates. Okay, we don't have time for the other things. Okay, so what does coordinates means? Okay, so again, we always start our discussion with a vector space. This vector space can be any vector space. Okay, it can be the vector space of polynomials, of the matrices, or the usual vectors. Doesn't matter. And we take an ordered basis. Okay, so this is a new term, ordered basis. So what does it mean, ordered basis? So so this term is important, ordered basis. So let's take it like this. So these are vectors v1 up to, let's say, vn. Okay, what do we mean by ordered basis? Ordered basis is actually, it's a basis, the first thing, and the second thing, the order of the elements is important here. Okay, so we don't change the order of vectors v1, v2. Okay, so the order here is important for our discussion. That's what ordered basis means. Okay, so S is an ordered basis. Then what can we do? If we take any vector, in V, then we know that since the span of these vectors is the whole space, we can write V as a linear combination of vectors in S, right? So if we take any V, we can write it like this. Here, A1 to AN are scalars, or in other terms, they are real numbers, okay? Because for us, scalars always mean real numbers. Okay, now our definition is this. So we define something called V sub S, okay? This S is the same as here, this S, okay? So this S is what we mean here. So this is the vector. This means the coordinates of V with respect to this ordered basis. So how do we define it? Well, we define it as these numbers, A1, A2, and AN. And the definition is this. Coordinates of V with respect to what? The set S. Okay, that's what it means. So yeah, that's what it means. So let's let me give you an example. For example, let V be R2 and the set S be, well, let's take it as I don't know, 1 0 and 1 1. Okay, so we can show that this is a basis. Okay, you can easily see that this is a basis, and this is a, let's take this as an ordered basis. Oops. Then what do we have? Okay, so what is the question here? Let's find, let V be the vector, I don't know. Let's take it as 3 and I don't know, 2. Then the question is this: what is the coordinates of V with respect to the with the spaces S? So this is the question. The solution is like this. Let's write the solution. So what do? We write the vector 3 and 2. Then we write A1 times 1 0 plus A2 times 1 1, right? And this is a very easy equation to solve. If you look at this, this gives us A1 plus A2, and the second line gives A2. So we get what? We get A2 must be A2 must be 2, and if A2 is 2, A1 must be 1, right? Okay, so the coordinates of this vector, oops. The coordinates of the vector V with respect to this ordered basis is A1 and A2. Okay, so what is this actually? Let me give some idea about this. This is all this is saying is uh, all this is saying is to obtain the vector 3, 2, to obtain the vector 3, 2, let me do, oops. So go 1 unit in the direction of the first vector 1, 0, and then go 2 units in the direction of the second vector 1, 1, right? That's what it means. So this vector, the coordinates of this vector is 1 unit in this direction. I'm doing the same thing, and 2 units in this direction. So that's what coordinate means. It's meaningful, I think. Okay. How do we determine the basis is in the correct order? There is no such thing as correct order. Okay, so if we change the order, so either the problem we are using, we are dealing with gives us an order, or if you're doing our own application, we fix the order at the beginning. Okay, so for example, if we changed, so let's look at the same problem. So let's look at the same problem, but this time let's just change the order of the bases, 1, 1, and 0, 1. Then the coordinates of the same vector, the coordinates of this, the vector 3, 2, with respect to this basis S, it will change, right? So it means this time you have to go 2 units in the direction of the first vector and 1 units in the direction of the second vector, okay? So here the order changed. There is no such thing as a correct order. Okay, so that's it. What else do I want to say about this? So, okay, so let me talk about this thing. So if we have, okay, again, I have this ordered basis, V1 to Vn, right? So if I have, if the coordinates of a vector with respect to S is A1 to An, and if the coordinates of another vector with respect to S is B1 to Bn, then what is the coordinates of the vector V plus W with respect to S? Okay, we will show that this is actually A1 plus B1 An plus Bn. Let's see why. Okay, so what does this really mean? What does this really mean? This really means this thing. So when I'm writing V plus W, the coordinates of this, oh, sorry. I want to write this. Okay, this is very easy, right? So this means V is really A1 times V1 plus An times Vn. And this thing means the coordinates of W being the B's means W equals B1 times V1 plus Bn times Vn. So what is v plus w? Well, this is just I can write these. I can add these vectors to obtain this. This is straightforward, right? But what we write at the end is really this. So it shows that the coordinates of v plus w, oops. Okay, so v plus w is really these numbers. Okay. Any questions here? Another property is if C is any real number, then we can show that the coordinates of C times V with respect to the spaces S is C times the coordinates of V with respect to S. So this is, proof is similar. So I skip it. Okay. Any questions here? No. Balan. Okay, so let's try to do something about transition matrices. So I'm skipping parts of this section, okay? So we're not doing all of section 4.8 because we don't have time. Let's talk about these transition matrices. So what does transition matrix means? So suppose suppose we have not just one ordered basis, but two ordered bases. Basis. So the plural of basis is still basis. V1, Vn. So this is, let's this be a ordered basis, and let T be another ordered basis. So it's, let's call these vectors V1, W1 to Wn. Okay. So since these are the bases of the same vector space, they must have the same number of vectors. If one has n vectors, the other must have also n vectors. So we have these two ordered bases. Let me write the plural of bases. Bases. Okay, so be careful about this letter E. So it's not I, but E. So the plural of bases is bases. Anyway, so what we are trying to find is this. So first let's look at the coordinates of this vector with respect to the basis S. This means C1 times V1 dot dot dot Cn times Vn. So what does this mean? This means the coordinates of the vector V. Oh, I want to do this for W. I'm sorry. So let these be W. Okay, so what does it mean? This means that the coordinates of V with respect to this basis T, ordered basis T, is this column vector C1 to Cn. Okay. Now I want to see the relation of the coordinates of this vector v with respect to t and the coordinates of v with respect to s. What is the relation between these two things? Is there an easy way to pass from one coordinates to another coordinates? Okay, this is my problem now. So let's look at the coordinates of v with respect to s now. Okay. So I know that the vector v can be written like this. So we can write it like this, plus Cn times Wn. Okay. And from our previous discussion, we have seen that I can separate this into products, into sum like this. So I'm using the idea that sums and scalar products can be separated like this. Okay, Cn times Wn s. Okay, so this is, I can write this thing as a matrix and as a matrix product. How do I do this? So as the first column, I write this W1, the first basis of T in terms of basis S. The second column is W2 S, and it goes like this. And the last one is this, times what? Times C1 times C2 times Cn. Okay, so if you're confused here, this is something we defined maybe the second week of the class, and we never used this one. So let me remind you what I'm doing here. Let me remind you here. So what I'm doing is I'm writing what am I doing? What am I doing, guys? Okay, let me give you an example to see how this works. So suppose A is A, B, C, D, and the vector X is, let's call this Y and Z. Then let me write A times X. What is A times X now? A times X is, if you compute this, you get AY plus BZ, right? And times CY plus DZ, right? And I can write this as Y times AC plus Z times BD. Well, what is this? Look, this is the same idea as here. It is the first component. So the first component here is multiplied by the first column you see here, and the second component is multiplied by the second column. So this expression is really the first component multiplied by first column you see here, and the second plus the second component multiplied by the second column, so on and so forth. Okay, same thing. Soru çözüyorsunuz hocam. Ne demek istedin Can Gök? Okay, so this is a reminder. Okay, so this is a reminder. Let's write reminder here. Okay, guys. So this was a reminder. Now let's look at this thing. So we will give a special name to this one. So this thing will be called transition matrix. Transition matrix from the T basis to S basis. Okay, so it will be denoted by P, S, and T times. So what is this guy? C1 to Cn. So we gave a name to it, right? So its name was Vt. So this guy is really called V sub T. V sub T. Okay, so here this guy is called, let's write it, it's called transition matrix from the T basis to S basis. Okay, so let's make this so this is called transition matrix. Okay, let's try to do some examples about this. Olmadı Can, hiç olmadı. Anlaşılamadı. Ama güzel bir çabaydı. Tebrik ediyorum. Okay, let's look at an example. For this example, let's work with a simple example, okay? So let's work with something in R2. So let's write two bases for S. Let one of them be, I don't know, like 1, 0, and 1, 1. And the second one, let the second one be what? I will use another one. Let this be 0, 1, and what about this one? Let's take it as 2, 0. Is that fine? No. Let's take it as -1 and 0. Okay, so this is a easy example. Let's work with an easy example. So the question is what? The question is find a transition matrix from T basis to S basis. So what is this? What is this? Okay, guys. Now, for this one, so these are our W vectors. So this is W1 and this is W2. And this is our V vectors, V1 and V2. So what I should do is compute W1 in terms of V vectors. So I have to write it as C1 times V1 plus C2 times V2. So what does this give me? What is W1? W1 is 0 and 1. So it is C1 times 1, 0 plus C2 times 1, 1, right? So this is what? C1 plus C2. And what is this? C2. So what is C2 now? C2 is 1. What is C1 now? C1 plus C2 is 0, so C1 must be -1. Okay, so we found the coordinates of W1 in terms of the basis vectors S. So it is C1 and C2. So which means to obtain W1 vectors, to obtain 0, 1 vector, I have to go -1 units in this direction and then go 1 unit in this direction to obtain it. Okay. And I have to do the same thing for W2. Okay, let's do it for W2. For W2, again, let's write it C1 V1 plus C2 V2. And this will give me what? What is W1? W1 is -1 and 0. So I can write this as C1 times V1 plus C2 times V2. Okay, C1 plus C2 and C1. No, C2. So this gives C2 must be 0, and if C2 is 0, C1 must be -1. Okay, so the coordinates of the second guy, second vector with respect to S basis is -1 and 0. Okay, so this is good. Now we can write the transition matrix. What is the transition matrix? Transition matrix is, we write it like this, from S to T. So this is, as the first column, I put this guy, -1, 1. And as the second column, I put this one, -1 and 0. Okay. Now, how does this matrix, what is the use for this matrix? What does this do? This matrix, so if you take a vector and compute its t coordinates, then to compute its s coordinates, all you have to do is multiply by this, the t coordinates of the vector by this matrix. Okay, so let this be part A. Okay, so as part B, if the v if the t coordinates of a vector is, I don't know, 2 and 3, then what is, then find find the s coordinates of it. Okay, how do we find it? So what we have seen is, to compute this guy, to compute v sub s, all you have to do is multiply the t coordinates by this matrix. Okay, so this will be -1 and 1, 1 and 0, and then 2 times 3. Okay, that's it. So this will give us what is this? -2 plus 3, which is 1, and plus 2. So the s coordinates of this vector, so we are given the t coordinates, and the s coordinates is just this. Okay, so this transition matrix really makes this very easy to change from one coordinate to another one. Okay, let me see if you have any questions. Any questions, guys? Evet, biraz burada bundan sonra yeni konuya geçeceğim arkadaşlar. Biraz burada durup soru sorabiliriz, konuşabiliriz. Okay, I'm waiting for your questions now. Any questions? Okay. You can still ask questions, but let me write another. Planlanan müfredata göre önde miyiz? Yok, önde de değiliz, geride de değiliz. Normal yerdeyiz. Geçen sene burayı çok fazla anlatmamıştım. Normal. Herhalde bayramdan sonra ders olacak mı bilmiyorum. Program nasıl olacak? Ama yani bayrama kadar normal geçen sene işlediğimiz konuları bitireceğiz. Yani bu hafta, gelecek hafta ve ondan sonraki hafta toplam 3 haftamız var diye düşünürsek 3 haftada planlanan konuları bitireceğiz. Eğer zamanımız olursa bayramdan sonra ekstra örnekler çözeriz. Daha şey de belli olmadı, yani nasıl bir sınav sistemi olacak mı olmayacak mı? Ne yapılacak onu da bilmiyorum. Belki ödev sistemi olacak, bilmiyorum artık. Efendim Can Gök. İlk konulardan itibaren mi? Ne olduğu belli olmadığı için sorunun cevabını da bilmiyorum. Okay. So let me write this example, and if we have time we can solve it now or we can leave it to... Yani daha çok son konulardan itibaren soru çözelim eğer zamanımız olursa. Okay, let the vector space be P1. What is P1? Oops. What is P1? Okay, I think I lost this one.